curves defined by parametric equations. You've actually met parametric equations before. We're just going to do a little bit more work and, you know, a little bit, what's the word I'm looking for? In a little bit more detail. So to give you an example of what a parametric equation looks like is you describe the position, the XY coordinate of something, in terms of a new variable called t. And if you wanted to sketch such a curve, you could simply do it by hand. Not that anyone really would, but we're going to do it by hand just to show you how it would start. There's the X and there's the Y. So let's suppose I do, I don't know, the first three, right, after 0. Right, so when when t is 0, this guy's 3, this guy's 0. When you put t equals 1, this is 4, and that's still 0. You put in 2, you get 7, you get 6, you put in 3, you get 12, and 24, and so on, right? Now, these are just snapshots, right? Because 0.5 would have a point, right? 1.1 would have a point. And what you could then do is you could plot the points. So when t equals 0, it was at 3 0. At t equals 1, it was 4 0. At t equals 2, it was 7, 6, it was here. And at 3, of course, I don't have scale, so it's over here somewhere. 12 and 24. So you can imagine it might look like that, right? And one thing that a parametric curve, that a normal curve doesn't have, is it has orientation. Do you notice that this curve is being drawn with arrows, saying this is how you travel along the curve? And because t equals 0 to t equals 1 to 2 to 3 to 5 to 7 and so on. So when you sketch a parametric curve, you also should be indicating direction. Its fancy name is orientation, right? So you should be giving its orientation. One of the uses, main use, though there are others, is that a lot of curves or a lot of movement can be designed in terms of parametric. And that's why that's called t, because this typically is time. So you can see at t equals 0, at t equals 1, at t equals 2, you know, and t equals 3 and so on. You get a kind of snapshot of a moving object through time. So far, so good. Right. So I'm hoping that you remember doing some parametric stuff a way back in trig. You might not have done a lot, but do you remember doing some of it? So the kind of things that you're going to get with parametric are, number one, graphing it. And there are two ways to do that. One, we've just shown you a table of values. Two is going to be using Desmos. So let me jump over and show you how you would use Desmos to do a sketch, right? To draw a parametric curve. Give me a few minutes. Okay, where are you hiding? Okay, we're good. There. Let's click on Desmos Parametric. Yay. Okay, and this one is just set up, but essentially it tells you how you would do a function, and I'll do it down here. You simply just do a bracket, and in the first one you put, in this case, what's it, t squared. That's not what I wanted. T squared. Why are you doing that? There we go. Don't know why it was being a pain there. T squared plus 3, comma, t cubed. There we go, t cubed minus t. Put a little bracket. It's not uncommon that you would draw your parametric, let's get rid of these guys here, that you would draw your parametric, say, from t equals 0 to t equals, let's say, 3. And there you go. If I shrink this back a little bit. There. Would you agree that looks very like the one I drew? Maybe a little bit better scale, but that's how you draw it. That guy there is, if you want to plot, not I would, in this case, a single point, it's a coordinate. Okay, so I'll copy this as my template. Suppose I wanted to do three sine t and do 2 cosine t. And I'm going to do 0 to 2 pi. It's not what I want. There we go. Make that guy go away. There. An ellipse. So whatever is x goes here, right? And whatever is the y goes here. And there's typically going to be a start and a finish. Zeros seems to me to be a natural starting point, since t very often means time. So t equals 0 is starting the movement, and then 10 would be whatever, 10 seconds later. That seems pretty straightforward. If you want to draw a parametric Desmos, there's your guy. Let's move on then and talk about other things that you could be asked to do with a parametric curve. And I'm just scanning through these right now. Almost every question that I'm looking at least in the start, they're all just sketching things. Now, one of the things I did notice in Desmos, which I didn't pay attention to, it came to me right now, is suppose you go to Desmos and the curve looks like this. What you'll get in the homework is 4 graphs. And one of them is going to look like this, and the other is also going to look like this. But one of them is going to be going up the way, and the other one is going to be down the way. What Desmos doesn't tell you is what direction is the right one. So if you want to know whether you go up the way, because it could be, couldn't you start here and like go down the way? Couldn't that be the orientation? Then a simple way would be just to find out where it is at t equals 0 and find out where it is, say, at t equals 1. So let's just say, for argument's sake, it was here at t equals 0 and it was here at t equals 1. Do you see it's that arrow? Whereas if it was here at t equals 0 and then it was here at t equals 1, do you see how you can orientate it that way? You might just be able to do it in your head. T equals 0 is very often easy to calculate, isn't it? So, you know, you may not need the second one, because if that's 0, isn't it kind of obvious where it has to go? And if this is 0, it's kind of obvious where it has to go, right? But you do need an orientation, because I'm looking at it right now and they tend to give both versions of the shape, one with the arrow going up and the orientation one where it's going down. Second thing is you're going to do some algebra, and that is a process called eliminating the parameter t. So you've drawn the thing, you've picked the right picture, and now your job is to eliminate the parameter t. So here is x, and here is y. And the process of eliminating the parameter t basically means find out an implicit equation. So you're going to find out, what the curve looks like in terms of x's and y's. It probably won't be, for many cases, a y equals, but it will be one of these jumbled up x and y things, right? And there are, in many cases, there's going to be more than one right answer. But hopefully you get the same one that WebAssign is looking for. Or if WebAssign's really clever, it'll have 2 or 3 right answers and you'll pick one of them. But in many cases, there's probably one obvious one to do. So this is this is the steps that you would do to do it. Step 1, identify one equation. It can be either the x or the y, it doesn't matter. That is simple to convert into t equals some function of x. Now, I've got a choice here. I'll put names on them. X is equation 1, right? And y could be equation 2. Looking at those two equations, most of the time there's going to be one guy who's just easier to do than the other. Which of those two equations do you think you could rewrite and solve as a t equals?
The first one.
Right, correct. What was your thinking? Why?
There's only one t variable within it.
That is a very good point. If there's only one t in it, I would probably go that road, right? Now, if both of them have one t in it, you go to the one that looks like it's the t's easier to suck out, right? If it was 2t plus 1, and the other one was e to the t, minus 40 or something, pretty easier to do the first one, right? That would be a suggestion. So let's choose that one. Well, whatever way you want to do it. I'm going to add t squares to both sides and take away x from both sides. And then I'm going to take the square root. And I'm going to just make the assumption here that t is positive because t is time. I don't want to do a Doctor Who going back in time thing. Now, step 2. Use your t equals f of x guy from step 1. And, well, what do you think I'm going to do with it? I've got t equals the square root of 1 minus x. What the heck am I going to do with it?
Plug it back into the second equation.
Yeah. In that case, right? So we are going to have y equals 2t plus t cubed. Are you comfortable with that? So after you've drawn a sketch using Desmos, nobody would really ever use a table of values. Would you agree that once technology takes over, table of values is kind of redundant, right? But it's there just as for completeness sake. So let me, oh, by the way, the one I just did there was a version of question 2. So let's see if we can eliminate another one. Maybe we should pick this one for him. No, that's pretty similar. Won't do that one. Okay. This is a version of question 5. X equals t squared and y equals, in my case, t to the n. Now, this is an example where there are two different looking answers, but they're essentially the same, right? They're equivalent. So which one do you want me to use? 1 or 2 is my step 1. Identify the simple convert thing.
1.
1 again, right? Now, if you do 1, can we just cut to the chase and say that, assuming that t is positive again, right? And then if you plug it into here, you get the square of x to the power of 8. And of course, style points is always part of everything, right? You know the square of x raised to the power of 8 is a pretty yucky way of writing something. So how would you use it? How would we write it, I should say?
1/8.
Say that again?
2/8, right? Or 8 to 8 or 2.
Not sure. Okay. If I write it that way, does that give you a better idea of what I'm expecting? X to the 1/2 raised to the power of 8. What does that simplify to?
X to the 4th.
And there is your answer, which is a very nice equation, right? And nothing particularly scary going on there. And I said there was 2 answers. Well, if I decided, because I felt like it, to do that, then wouldn't t be the 8th root of y? And then if I go x equals t squared, it becomes x equals the 8th root of y squared, which if I call that 1/8 squared, you then essentially, if you raise something to a power, you multiply the exponents. So that would get you 2/8, which is a quarter. But in style points, you get that guy. Now, in this particular example, I think it's quite obvious that that guy and that guy are the same guy. You could almost convert them. In some of the later choices, the 2 answers will be so different looking that you won't really be able to tell for sure that they are equivalent. But if you did the math, they are, right? If you did the math, they are, even if they don't look like it. Now, sometimes we rewrite our equations using theta instead of t. Very often that's because of things called polar, but they don't need to be because of polar. So suppose I had x equals the cosine of 2 theta and y equals 8 times the sine of 2 theta. Now, when you are dealing with trig, your process is going to be different. When it was, t squared and t cubed plus 1s and all that, this method here, fine. Whenever you get sines and cosines, or trig in general, but sines and cosines in particular, you have to approach these differently. So I'm going to take equation 1 and I'm going to divide it by 8. So I'm going to isolate the cosine. I'm going to take equation 2 and divide it by 8. And that's going to isolate the sine. So if you ever see a sine and a cosine combination, and we'll assume that these are the same because they have to be, what you're then going to do, once you've separated these 2 guys out, is you're then going to square everybody. you okay with that? That if x over 8 is a cosine of 2 theta, won't x over 8 squared be the cosine squared of 2 theta? Now we're almost done. But now you have to think outside the box. What am I going to do next?
Do you remember the formula of sine square plus cosine square equal to 1, right?
Okay, so why don't I just add these equations together? In which case, if you take this guy, and I'm just multiplying it out, and you take this guy, and I'm just multiplying it out, and isn't sine squared plus cos squared equal 1? Sine squared 2 theta plus cos squared 2 theta is 1. Sine squared t plus cos squared t. As long as it's the same guy, and one's a sine squared and the other's a cosine squared, you get that. Looking good? No more thetas, just x's and y's. One more line. Can anybody see a style point?
You separate that 64, or you multiply on both sides,
Yeah.
and then take the square root of it.
Oh no, don't do it anymore. Just do that. You can't take the square root of that and call it x add y, because two things added do not get simplified inside the square root. So you can simplify the square root of 3 times 16. You can't simplify 3 plus 16, right? So that's the answer. There is no more you can do. Does anybody recognize that guy?
Equation of a circle?
Yeah. So that particular parametric equation generated the circle. That one that I just did is an example of question 6. Let's find a different trig one. Suppose x is 4 sine theta and y is 3 cosine theta. Okay, let's work on this situation, right? It's very similar. We're going to do it in a very similar way. What should I do next?
Divide
you
out the
make-
constants.
Okay, divide out the constants. So divide everybody here by 4 and what, divide everybody here by 3. That's a good start. I like that. What's next?
Square them both.
What's next?
Find them.
Okay. That guy gets you x squared over 16. This guy gets you y squared over 9. And this guy gets you 1. We're actually finished here. There's not anything style points you can do here that is worthwhile. Does anybody recognize who this guy is? Anybody know what this is, what kind of curve this is an equation for?
Does that Pythagoras? Pythagoras, right?
It looks like something to do with Pythagoras, like x squared plus y, but it's not. That's not what I'm asking. I'm asking what curve would you get if you plotted all the points where the x coordinate squared plus 16 added to the y coordinate squared plus 9 was always equal to 1.
An
Last
oval?
chance. Say again?
An oval? I forget
Yes.
the other term.
It's called an ellipse, but you're right.
Yeah.
It would look something like this, where these would be 4 and these would be 3. A lot of objects moving in space have elliptical orbits, don't they? And parametric equations, if you make that t instead of theta, parametric equations allow you to plot an object orbiting, say, the Earth orbiting the sun, right? Because it's on a plane, so you could think of it as 2D. If you're thinking, what does the theta tell you? It just tells you this angle here. So you can watch an object, you know, in terms of the angle it makes with the x-axis. Now this guy here has got a twist in it. So it's always a good idea to not get too, you know, everything's written in stone and this is the only things you can do. This one is kind of like that one, but it's different enough that you have to do a little bit different stuff. Any suggestions for what we would do to eliminate the theta?
Take the square root of the x function to get the square root of x equals 2 sine theta.
I'm not saying that's wrong, because actually I never thought about doing that, but I'm not sure what the benefit of doing it is. I'm not sure what you do next. So
Would you be
I'm
able
not
to
saying
keep the x as it is?
yeah, pretty close to as it is. A little tweak to it, but pretty much leave it alone. So what do
But
you think you
just
might do?
Divide out the 4 and leave the
Okay.
sign.
Agreed? Now, what about this guy? What should we do with this guy?
Should we square it?
Yeah, but probably we should divide it by 5, right? And then square it. So do you see we just adapted the strategy to accommodate, you know, the situation in front of us, right? So that guy's already a sine squared. Why should I do anything to him? He's good. I like sine squared. So if you add them, you will get x over 4 plus y squared over 25 equals 1. And there's not a lot you can do with that, so I would probably just leave it alone. What does that look like? I think that's a hyperbola. No, it's not. I have no idea what that is. I think it's something to do with, you know, a big happy face on its side. But unless I actually put it in to Desmos, I couldn't tell you what shape that is, but it exists. This one does not require the method we just used. This one is a brand new situation. So kind of clear your brain and take this fresh. Any thoughts?
Well, secant is the inverse of cosine, so
Reciprocal's the word, but I know what you mean. So it's equal to that. Okay. So I'll put a little line. I'm going to write x underneath it. Okay, so these are our new equations. So forget about them. Keep thinking. Where are you going now?
Square the x cosine.
So which equation do you want me to work on, Jeremy?
The x value.
And what do you want me to do? Square it, did you say? Okay. So I've got x squared is 49 cos squared theta. I know you don't need to do this every time, but I think it just helps. Right. Nothing wrong with this strategy. It's getting there.
Can you divide the cosine on the x to make it look more like the y?
Oh, you mean like work on one to make it more like this?
Yeah.
I think you would end up algebraically being in trouble
What if we do the inverse for the y?
So the word reciprocal, I agree.
Sorry.
Just try and get you, there we go. If this is true, isn't that true? Actually,
And we wait, hold on. We have a
let me write
cosine.
it this way. There. Not what you just said, if that's what you meant, works fine.
So just bring over the 49. We'll divide out the 49 and combine like terms.
Okay, so if I pick you up correctly, we're going to do nothing to this. And then we're going to do an x squared over 49 is this guy. And when you say combine, are you saying if this is equal to that and this is equal to that, then this is equal to this? Right? Both of these are equal to cos squared. So the logic is this guy is equal to that guy. Oops. So yeah.
Sorry. Couldn't you have just multiplied the two equations up above to just get yx squared equals 49?
Oh, let's try that
With
strategy.
the cosine squared and the 1 over cosine squared canceling out.
So at what line? At this line here? Okay, so if I pick you up correctly, you've got, oh dear, let's start that page again. I like your thinking. So we've got this guy. And we got this guy. And if you multiply those two together, and you multiply these two together, don't you just get 49? I think that's what you said. Agreed?
That was the idea.
And that works. Now, wait a minute, that's not him. Well, actually, if you do a bit of work on him, he is him, right? There's another starting right at the beginning. Right, so this is us before we did anything. If you take this guy and you divide him by 7, you get cosine theta, right? If you look at this fella, he's 1 over cosine squared theta, which makes y 1 over this guy squared. It's a bit messy, but and that leads you to this fella. And this fella is also him. He is also him. You see, the problem with WebAssign is it may be looking for that one because it's a piece of software and it's not a human being. I like the look of this one myself personally, but if you can see a version that is y equals, you probably should write it down first and then let WebAssign, check it or not. I think the moral of that story is, isn't there different approaches to these questions? Algebraically, it's really just a matter of getting something that works. And people maybe aren't as comfortable with triggers, and they should be. But it is possible to do it. So I'll show you another one. And this is a version of question 8.
Oh, by the way, that one shape that you were wondering about, it's sideways parabola.
Oh, is it? I thought it would be something like that.
Yeah, it's back. It's the other way. It's facing the other way.
So something like that. Yeah, doesn't surprise me. This guy here, you deserve brownie points if you can tell me how this one's going to work out.
Is that cosine over sine?
That is cosine over sine, yes. But how are we going to solve this one?
Do it like the one above and just multiply everything out to get sine times cosine over sine times cosine.
Well, this one is only 1 over a sine, and this isn't. So I'm not sure that would work.
Yeah, never mind.
That was good thinking.
Solution, can we just separate all the term on the 7 cotangent out?
As a separate sine and cosine,
Like 7
And-
times cosine time, whatever down in the denominator?
in some questions, that would be the right thing to do, but not in this one. Trig, you know, they're different versions of trig. Here's a clue. Cosecant squared, take away cotangent squared is 1. Maybe it's probably not an identity that you're used to because it's not a typical one. Now, if I told you that, so if I said to you hint, which if I ever did this question, that's what I would definitely have to do because it's unfair to expect you to memorize every trig identity. Let's return back to these questions and see how this property can help us solve the question. So what do you think I should do to equation 1?
Just
Say again?
square it.
Square it, yes. What do you think I should do to equation 2?
Divide both sides by 7 and then square it.
Okay, now if you divide both sides by 7, square it, can you cut to the chase, you would get that. Now just one more line and you're there. What do we do with these two?
Subtract y from x.
Top from bottom. So once you knew that, this became a lot easier, didn't it? Well, let's leave trig and work on other things in algebra. Let's look at question 9. Right, clear your minds. Tackle this one totally fresh.
Use a natural logarithm.
Yes, that method would work, and it wouldn't be wrong, but it's not the most efficient way of doing it. But it would work, and nobody would take points off if you went that route.
Do we multiply them to get 1?
Oh. I should have gave out brownie points, but I forgot. Yes. Now, that might look weird, but technically when you multiply things, don't you add their powers? Isn't that a very pretty answer? Now, if you went the road you were suggesting, Jeremy, and it would have worked, would you agree it probably would have went to some really scary places first? So, not that it's wrong. I want to emphasize that. If it's the correct answer, even if it doesn't look like that guy, it's still correct. And since you were so keen on doing natural logs, here's a question with a natural log in it. Right, clear your mind, starting from scratch, everyone's unique. Your strategy depends on what you've got in front of you. So this is what we've got in front of you. I can think of 2 totally different ways to do this one. and you might well think of a better way. I'm going to, I'll just listen and see what we get. Any suggestions?
E to the x equals t.
Okay, I like that. So you're raising both to the power of a. So there's equation 1, and this is equation 2.
Y over 7 squared.
So y equals 7 square root of that guy.
I was going to do y equals square root of t, and y over 7 squared.
Oh, you're going to square those guys? All right, there's yet another way to do it. Okay, what are you going to do next?
If I add the 49, then substitute.
Okay, so you're going to get e to the x equals y squared over 49. Okay, that works. Anybody got another starting point, a different way of tackling this?
The same thing he was, but just opposite.
Okay, a little bit more detail.
Yeah, instead of getting my value for t off the x equation, I did it off the y.
Okay, so if you divide by 7, you get this guy. And if you square everybody, you get this guy. So I'll call it equation 1. Doesn't matter who you call equation 1 and who you call equation 2. And there's equation 2. And are you just basically going to plug that guy in here now? I think that's where you're going. Something like that. Although there's probably other versions. That guy's right. That guy's right. That guy's right. Can you see the fun you're going to have when you go into WebAssign and you do this one, but it wanted that one, or you did that one and it wanted this one? If you use up all 5 guesses, email me what your answer was, and I will look at it. And if it's correct, I'll just give you the points, right? This is not guaranteed, but I'll make an assumption. If one of them can be written as y equals, that's probably the one WebAssign is definitely looking for. Hopefully WebAssign will understand all 3. But if you have a choice, find one with a y equals. So far, so good. Well, that is the end. Sorry?
These are pretty fun.
Yeah. The challenge is I'd like things where it's not the same question 42 times, right? I mean, although it's the same basic question, wasn't the way you solved it kind of unique in lots of different questions? And not only is it kind of unique, there was more than one right way.
It's a lot better than taking 10 derivatives.
Okay, I got bad news for you now. We're now about to do our second section here. And that's going to be section 10.2. And we are going to be looking at the calculus of parametric curves. Actually, it's the calculus of parametric and polar curves, but that's far too long to fit in the labeling of the homework. Okay. It's actually not too bad. Imagine I have a parametric curve. Many parametric curves cannot be rewritten back as, x's and y's like we just jumbled, right? You cannot eliminate the parameter t from that. You cannot eliminate it from that. There is no combination that you could use. So there are many curves out there that cannot ever be written down as, x equals the cube root of y, blah, blah, all that stuff, right? Nonetheless, they do exist, right? They are curves. And I'm going to show you because I'm just kind of curious myself now, what this horrible thing looks like. And then we're going to find its derivative. You might be amazed at how they find the derivative of those guys. So I'm going to go in here, and it's a t cubed plus 2t. And then it's a 3t squared take away e, the t. And we'll do, well, how big is this thing? That's the question. Oh, good. There. Right, I like that. Okay, so t equals 0 to 100. 10. That's pretty, right? Right. So if I zoom back, basically, you know, it's just a curve, isn't it? Not the most weird looking curve in the world. Now, at any given point on a curve, let's say at 10, you see at the 10, 4, right? That point there has coordinates, I think, 10, 4. Right? Would you agree there's a tangent line there? And if there's a tangent line, it has a slope. And if the slope of the tangent line exists, doesn't that mean it has a derivative at that point? So what I'm getting is parametric curves have derivatives. Roughly, I'm not saying for sure, but roughly about here, which is about 28. Would you agree there'd be a horizontal tangent line? Right, top of the hill. So parametric curves have the exact same properties as any other curve. The problem is finding the derivative isn't the same way. So here it is. The notation that I'm going to use for the derivative is dy by dx. Right, you've used that notation, right? Derivative is called dy by dx. And here is the formula for it. Isn't that amazingly simple? You only differentiate the y with respect to t, and that gets you 6t take away e to the t. And you differentiate this guy with respect to t, and you get 3t squared plus 2. So when you differentiate a parametric equation, the answer you get will also contain t. Does that make sense? So if I wanted to know what the slope of the tangent line at t equals 0 was, right? Then I would find the derivative. You put a little vertical line and you put t equals 0. That's just a notation to tell people what you're doing. And in this case, it would be 6 lots of 0, take away e to the 0, over 3 lots of 0 squared plus 2. That's 1, that's nothing, so that's -1. It'd be -1/2. So would you agree I can find the slope of a parametric curve anywhere I like? It's just that the answer will be in t's. And when you want to find the point on the curve, won't you have to tell me the t value, which makes sense, right? For parametric curves, you tell me where something is by telling me t. So couldn't I find it at t equals 1 and t equals 21 and so on? That makes sense? Any questions? Is that so far so good? So let's just do some practice at finding derivatives of parametric curves. First derivatives. Let's move on. bouncing around here because I can't find my Do you notice how I didn't swear there? Right, back me up, Caitlin. Did I swear there? No. Didn't I give some strange growling sounds, but that's it.
You said darn it, didn't you?
I don't know if I said that. I hope I didn't, but I might have. But that is nothing. There is a member of the math faculty who I've been told by other students sounds like he may have been a sailor at one time. When I get frustrated, I growl. Okay, I try to. I also do other things. If I get really annoyed, not totally annoyed because I swear, if I hit my thumb with a hammer, trust me, I'm swearing, right? But if it's below that level of frustration, I will say, oh, what will I say? Oh, bananas. I just say that. Right? Don't be shocked. It's a banana. How can anyone be shocked, right? And sometimes I'll say current bun. And that saves me swearing. So if you want to be in mixed company, do that. I can tell you who I can blame for this by being brought up by 6 sisters and my mum. And none of them like swearing, so they kind of beat it out of me. And now it's second nature to me. Okay, so let's pick a guy to find the derivative. It's 2t e to the t, and the y is 8t plus sine t. Now, as horrible as that is, its derivative is not that bad. It's dy by dt over dx by dt. Now, before I do this, I want to show you something. Do you know these? I don't know what I am. Can you actually see what I'm writing right now, guys? Oh, good, because I can't. Yeah. If you look at that, really, you could almost understand why it works. These are differentials, but in a lot of ways, don't they behave like fractions? And if you had this divided by this, wouldn't the t's cancel out? Can you see the dy by dx is left? Does that make sense, you know, why this works? Right. So this fella is 8 plus cosine t. And this guy in the bottom, well, I have to do a little product rule. So 2 times e to the t plus 2 times e to the t. Do a little style points by pulling out an e to the t. Actually pulling out 2 e to the t. And that leaves me with 1 plus t. Now, I do not know what that curve looks like. I could put it into Desmos, but I'm going to tell you what this derivative tells me about the curve. For starters, when you get tops of hills like that, won't the derivative be 0? Right? When I look at this function and I take this guy on the top and this guy on the bottom, would you agree that this fraction can never be 0? Let me argue why. If you have a fraction that's equal to 0, isn't it only the top equals 0 that matters? The bottom can be 42, it won't matter. Would you agree that the cosine of t, the worst it's ever going to be is -1? So if you add 8 to that, would you agree that 7's as good as it's going to get? Right? So that means this is never 0. So this thing doesn't have any hills in it. Now, when you have a curve that does this, if you choose a point here, won't its tangent line be vertical? Sometimes they describe it as the furthest right point. I guess you can understand why that's as far right as this curve's going to get, right? At least locally. Now, if that's the case, what will the value, if that's the right way to phrase it, What will a derivative be equal to when it's got a vertical tangent line?
Infinity.
Infinity. Okay, we can use that. Now, if you're going to get infinity out of a fraction, the top doesn't matter. Isn't the bottom going to have to be 0? So in that case, I need to find out, is there any values of t where that happens, right? And there is actually only one. And evidently, TARDIS moving is allowed, right? So at t equals -1 to, I guess that would be -1 second after you observed it. And that can happen. But what does that tell me? It has no hills and it has one right-hand point, or it could be, I guess, a left-hand point. So my best guess is, won't that curve look something pretty boring like that? Now, let me explain why you could have -1 as t. Can you imagine that you noticed an asteroid at this point here, right? This is the Earth. And you finally appeared and you got a picture of it. You would call the point where you first saw it t equals 0. And then you plotted where it is over a certain time period, right? And it did that, which is what you want asteroids to do, right? Whatever reason, right? So t equals 0, 1 year later, 2 years later, that would be the closest point, and so on. Wouldn't t equal -1 just be where it was 1 year before you saw it? So it's not necessarily going back in time, isn't it? Just a frame of reference. If you have a moving object, you can predict where it's going to be in the future, right? If you have enough points and you model it, right? But can you also tell where the damn thing came from? And most asteroids come from, God, I've forgotten what the thing is called. What that thing is called. What is it called? It's a something belt. I think it starts with
The asteroid belt?
Well, that's what it should be called, but it's called something like the Oder belt or the Uder belt. And it's a place where a lot of asteroids kind of live, and they get like billiard balls, one gets hit and off it shoots towards, in some cases the Earth. How do you feel about finding these derivatives? Are you comfortable with how to find them? Are you comfortable that you can tell me at what value of t it has a 0 derivative and at what value of t it has an undefined derivative? Right. 0 derivative is when the top is 0. Right. Vertical derivative is when the bottom is 0. Okay, I think we've got time for 1 or 2 more. Oh, this one will do. Question 3. And we have a t squared plus 2t and a y equals 2 to the power of t, take away 2t. And I like it because of that 2 to the power of t fella. What is the derivative of 2 to the power of t? Okay, that should...
2 to the t natural log of 2.
Well done. Did you just memorize that, or did you have a quick look it up?
You'll never know.
Oh. Then I'm going to assume that you looked it up and you don't want to tell me. It doesn't matter, but it's nice that you knew it. Right, and the other guy is what? 2t plus 2. And I don't think there's any style points worth talking about, so that's the end of that question. Let's do a trig one. Not so many trig ones. Okay. Question similar to 4. X is the sine of 4t. plus a cosine. That's interesting. And y is going to equal the cosine of 4t, take away sine t. And the first thing we're going to do is find its derivative. If you differentiate a cosine, you will get -4 the sine of 4t. And if you differentiate a negative sine, you will get a negative cosine. If you differentiate this fella, you get 4 times the cosine of 4t. And if you differentiate this guy, you get negative sine of t. And question B says, find the derivative at t equals pi. So -4 the sine of 4 pi, take away the cosine of 1 pi, and then it's 4 cosine of 4 pi, take away the sine of pi. Okay, the sine of 4 pi is nothing, and the cosine of pi is -1, so that gets you 1. Cosine of 4 pi is 1, so that gets you 4, take away nothing, so the answer would be 1/4. So the derivative, the slope of the tangent line, is 1/4 at t equals pi. And then they ask you, for the final part, find the equation of the tangent line. Now, it's okay to find derivatives in terms of t. Obviously, it's the most convenient way to do it. But when we return back to finding equations of tangent lines, we want things like this, right? The good old-fashioned y equals so many x plus or minus a number. So I'm going to take t equals pi, and I'm going to find the x coordinate that corresponds to. So it's a sine of 4 pi plus a cosine of pi. And that's 0, take away 1. So the x coordinate is going to be -1 at that point. And the y coordinate is going to be the cosine of 4 pi, take away nothing, which is 1, yeah, 1. So I am going to find the equation of a line that passes through -1, 1 and has a slope of 1/4. And we do that by the point slope equation. So y take away 1 is 1/4. What the heck? That's x take away, add 1. Y take away 1, 1/4 x plus 1/4. And we get that guy. So far, so good. So for this parametric equation, this curve here, the slope of the tangent line at t equals pi is going to be, if I haven't made any mistakes at least, 1/4 x plus 5/4. So I'm going to show you that you can actually check that in Desmos. Now you wouldn't want to check it normally, because WebAssign would do it for you. You know, it'd say you were wrong. But in this case, we do want to see if we can make that happen. So there we go. So it's sine of 4t cosine of t. And then it's going to be plus cosine of t. So let's done that one. So it's cosine of 4t. Take away a sine of t. Okay, and we're only interested in pi, so I'm going to do just this guy. Oh, would you look at it? Isn't that a cute little shape? Anyway, I'm only interested in pi here, right? So maybe I'll just make it to 2 pi. There. So that's what the curve looks like. Now, at the point we're interested in, it was at the point -1, 1. So I'm just going to do -1, 1. And that's, there we are. You see it's up here? Now, I hope it allows me to type in y equals 1/4 x plus 5/4. Are we good or are we good? Would you agree that looks like a tangent line at that point on this parametric? So even although parametric are weird, and that's very pretty and weird, can't we still do calculus on it? We can still find its derivative. We can still find equations of tangent lines, even in shapes that look decidedly strange. Last name down.